And we're going to take a look at 5.7 in the second part of class today. Okay, so we're going to start similarly with a bunch of rules, all right? So one thing we really want to be thoughtful about is that we are interpreting the rules carefully, and we're thoughtful about what might be coming up in the future as well, okay? So in taking a look at these formulas, these are ones that will end up with an inverse trig function. So like there's not inverse trig in the question part, but at the end of it, there is inverse trig, like after we've taken our integral, okay? And so let's start with this first one right here. So we have that the integral of du over the square root of a squared minus u squared is going to give us the inverse sine of u over a. And so I do want to address a few points because we'll see these letters u and a lot in these questions. And so I do want to make a note that a is a constant. All right, so I think Matt pointed that out earlier, asking for clarification, is a just a variable, but a is actually a constant, right? So it's going to be some sort of number. And then the u is some function with x. All right, so a is a constant, u is some function with x. And it turns out that if we have this integral of 1 over a square root and there's a subtraction in the middle, that corresponds to coming from this original function, inverse sine of u over a. And so if we know what our u is and we know what our a is, we'll be able to obtain our answer, okay? Similarly, if we take a look at that second rule, if there's no square root on the bottom, but we just have a squared plus u squared, we're going to end up with 1 over a, the inverse tangent of u over a plus c. Right? Now, I do want to put a circle around these first two. Right? These two are common in Calc 2. All right, so you'll see these, it'll be like at the end of a problem, you've done all this work and one of the parts might be an inverse sine or an inverse tangent, okay? The last one, which is nice to know, nice to see, is that if you take the integral of 1 over u times the square root of u squared minus a squared, you will end up with some variation of an inverse secant, all right? This one is less common. In Calc 2, all right? So if you're feeling like, gosh, there's just so many rules, think about the ones that come up more frequently. Those are likely to be the ones that sort of continue on with you in your mathematical career. And the ones that come up a little bit less frequently, maybe that's where you're like, I'm just going to Google it. I'm going to look it up on a table and it's going to be okay. But what better way to go through these rules than to practice them, right? And in particular, maybe contrasting some of these to the U sub that we saw in the last section, right? So we're going to start off with a definite integral. We're going to start off with a definite integral because I know how much we love trigonometry. And so anytime we can practice it a little bit more in terms of like, how do we find those sine or cosine values or the inverse sine or inverse cosine values, this would be a good place to put in a little bit of work. And so we can see from here that we might anticipate our solution being something with an inverse sine, right? because we have the square root on the bottom and then something minus x squared. Now, if we compare this to the actual formula that we have, we might say that we have this integral from 0 to 1/2 of dx over 1 squared minus x squared. And why would I sort of make it a point to say that 1 is 1 squared? Because obviously we know that 1 is 1 squared, but like, why would I write it as 1 squared? And why would I write x squared as like x in parentheses and then squared? And if we kind of zoom back into the actual question, we might see that in our answer, in that inverse sign, it is so important that we can find our u and our a. So what I've done by writing 1 as 1 squared is I've really said that a equals 1. And by writing x squared as x squared, I've really said that u is x. And then I can just plug things into my formula. Okay. So yes, the formula is useful, but we really have to identify what our u and our a are very carefully. And so in this case, we might say that u equals, let's start with the a. Our a equals 1, our u equals x, and this means that our integral is going to be our inverse sign of u over a, our absolute value of 1. And if we clean this up a little bit, we'll just notice this is the inverse sign of x. All right, so that's the first part. When I take that antiderivative, I'm going to get inverse sign of x. The second part is I'm going to need to plug in my bounds. And so this is really, I think, the exercise in this question is if I have my inverse sign of x, I plug in 1/2, I plug in 0, right? And so I want to be really explicit about what this inverse sign part is asking us, right? So this inverse sign of 1/2 is really asking us to find an angle that is between -pi/2 and pi/2, right? So we're looking for an angle, but it has to be between certain values with a y value of 1/2. Similarly, this second part is asking us to find an angle that is between -pi/2 and pi/2 with a y value of 0. And so if we think about that on our unit circle, we'll find that the first angle is going to be pi/6, and the second angle is going to be 0. And so we end up with an answer of pi/6. Now, it's been a little bit since we thought about what an integral meant. So this means that if I graph this curve, 1 over the square root of 1 minus x squared, and I look at the area underneath that curve in the x-axis from 0 to 1/2, that area will be exactly pi/6. All right. So don't forget, no matter how complicated this gets, all we're doing is finding area. We're either finding a function for that area or we're finding an actual numerical value. Okay. Now, I did get a question about these angle restrictions. Those are as defined for the inverse sign. That's the domain restriction for inverse sign, or not the domain, the range restrictions for inverse sign. Okay, so if you're not sure what those restrictions are, I'll try and make note of them here, but that's probably a good thing to sort of add to that list of like, things that tend to come up and are helpful to know, right? Along with like factoring and things like that. The angle restrictions for the inverse trig functions are fairly important when we're thinking about evaluating at a certain number, okay? All right, so let's take a look at the next example, all right? So taking a look at this one, example 2, we have the integral of dx over 1 minus 16x squared. And if you were to look back at the initial chart, we might say that this is an inverse sine situation, okay? And I'm going to write that we actually have a u sub situation here as well, okay? So here's what I mean by that. If we think about defining what A and U are, we can say that A in this case would be 1 because 1 squared is 1. And that U is going to be not 16x squared because U squared is 16x squared, but that would make U equal to 4x, right? And so what we need to do here is we actually need to accommodate for the fact that U is a different function. Okay, so it's not just an x. So we're going to find our derivative of both sides. We're going to notice that I only have a dx to sub, so I'm going to divide that 4 away. And then I'm going to go ahead and plug things into, make our substitution. So we'll get the integral, and I'll have a 1/4 in the front, du over square root of 1 minus u squared. Okay. That 1/4 here is definitely important. We forget to do the u sub, our answer will be off by a factor of 1/4. Okay. Now this is our inverse sine, so we're going to say 1/4 inverse sine of u over absolute value of 1 plus c. And we want to go ahead and make sure that we put our u back in. So we have 1/4 inverse sine of 4x plus c. All right. So not a definite integral this time. We didn't need to plug in our values. But if we did have to plug in some numbers for x, we would want to make sure that whatever our answer is, those angles fell, as we said in example 1, those angles fall in that quadrant 4 and quadrant 1. Okay. All right. Let me pause here for a moment. Are there any questions so far? All right. Let's take a look at number 3. So I've got the integral of dx over the square root of 4 minus 9x squared. And so I like to start by saying, what is my a squared? What is my u squared? And that way I can tell whether or not I'm going to need u sub to go through the question. So in this case, a is going to be 2 and u will be 3x. So a is 2, u is 3x. Since u is not just x, I'm going to need to do a little u sub situation here. And let's make our substitutions and see. All right. So now we're going to get 1/3 inverse sine of u over a. And a, keep in mind, is not 4, but is the square root of 4, so it's going to be 2. Last thing we're going to do, we're going to plug a 3x in for u. So we get 1/3 inverse sine of 3x over 2 plus c. And that is our solution for example number 3.
Professor, I have a quick question.
Yes, what's up?
You may have already said this, so maybe I just missed it, but so it's a squared equals 4, but why is u squared equal 9x squared? Actually, I just figured it out. My bad. I read it wrong. Sorry.
No, this is perfect. Sometimes we need to talk it out, and then we're like, oh yeah, that makes sense. Okay, so like the term in front of the subtraction sign is going to be our a squared, and the term after the subtraction sign is going to be our u squared. Okay.
Okay, thank you. Yeah, my mind tricked me.
It's absolutely fine. It happens to the best of us. All right. I will leave example 4 as one that you could do on your own. And I will tell you that you should arrive at an answer of this. Right? Example 4. So that can be one of your 10 questions if you wanted to use one potentially, but only if it involves u sub, right? If it doesn't involve u sub, then we don't want to use that for today's assignment, but this could be something that you come back to maybe to prepare for exam 4, okay? We had our chain rule and our u sub, right? So the u sub ones, I can't remember when those were due. Today, right? Yeah, I think it was, well, let's find out. Guessing games are bad when it comes to assignment. All right, so today is the 21st. Okay, so on Monday, I had you look at the chain rule review, right? And then tomorrow, let's do tomorrow, you're going to turn in a U substitution practice, right? So anything that's U sub that we haven't done in class, you can go to the notes and use those, or you can use some all the other resources for that. But the U sub practice is due tomorrow at midnight, okay? All right, so let's continue on our merry way. Oh, good. We have another one that asks us to actually plug in values for trig, right? Sometimes when we know things are hard for us, it's actually good to sort of embrace that and practice it and see if we can make it better. But in this case, I think there's a little bit less work to do on the setup end of things because we might notice that a squared is 1. So a is 1. U squared is u squared. So u is u. There's not a lot to unpack there, right? And that means that this integral is going to be our inverse sine of u, or u over 1, right? So there's a denominator of 1 because a is 1, but since we're dividing by 1, I'm just going to write it as a whole number and not a fraction. Then I have to plug in the √3 over 2 and the 0, okay? So if anything, I think the back end of this question is a little bit harder than the front end because we need to know what angle has a y value of √3 over 2 that is in quadrant 4 or 1. And then we have to find out what angle has a y value of 0 that is in quadrant 4 or 1. I'll give you a moment to find those values, all right? If you can give me a value for inverse sine of the √3 over 2 and a number for inverse sine of 0. Yeah, that first one is going to be pi over 3. And then the second one, let's see, where is the y value 0? That's going to be 0. And so we end up with a final answer of pi over 3. Okay. Now, what does that mean? That means if I graphed this function, 1 over 1 minus u squared, and I started finding the area from 0 to root 3 over 2, the area between that curve and the x-axis would be pi over 3. Okay. Now, I forget who asked this earlier, but we are definitely going to be going back to this idea of area. So I want us to just kind of keep in mind all these computations we're doing, like what does it actually mean? Why those two quadrants only? These are restrictions in the range of inverse sine. Okay, so I would make sure that you know your range restrictions for inverse sine, inverse cosine, and inverse tangent. All right, those definitely come up. Not super often, but when you need it, it's good to know it. All right. So let's shift gears a little bit, and we're going to take a look at some that don't have the square root on the bottom. In fact, they have more of like an a squared plus u squared situation. And so based on that, what trig function are we thinking might be the result for something like example 6? Good, yeah. And so we do want to be specific here that we are looking for an inverse tangent, right? So inverse tangent, yep, perfect. All right, so I like to set things up the same way. I like to find my a squared, my u squared. A squared equals 1, a is 1, u squared equals 4x squared, so that means u is 2x. In this case, because u is 2x, I'm definitely going to need my u sub, right? So I'm going to take my derivative. I'm going to make sure I divide that 2 away. So everywhere I see a dx, I can replace it with 1/2 du. And so this is going to give us an integral of, we're going to have the 1/2 in the front, the integral of 1 over 1 plus u squared du. And now it matches perfectly with our formula. And so we're going to have 1/2 inverse tangent of u over 1 plus c. So that 1 on the bottom is just the a, right? So it's not that we don't have it there, but eventually we're not going to need it because the absolute value of 1 is 1. And when I divide by 1, it's just a whole number. And last thing we need to do, we need to put back in our replacement for u. So I have that. As my solution for example 6. Okay. So lots of different things where we're using u sub in slightly different ways, right? And in fact, I think it would probably be a good exercise to perhaps leave example 25, example 7 here as one that you could potentially use. And I'll tell you your goal answer. Right. So you could go back and solve example 7 as part of your U sub assignment that's due tomorrow. Okay. So as you're picking your 10 questions, you'll notice that I was very open-ended, like choose 10 questions, work through them, blah, 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 that's it. But as you're choosing your questions, I would encourage you to be really thoughtful about where your strengths are, where you really want to grow, and how you can choose questions that will actually support that goal, right? I know you don't have to. I know you can choose the 10 easiest U sub questions out there and call it a day, and that's fine. But if you're looking to say, especially if you're going to Calc 2, I would really recommend choosing questions that are really targeting you and your learning so that you can really set yourself up to be successful in that next class. Okay. All right. Let's take a look at example 8 and 9. All right, so for 8 and 9, I think they're very similar. So we're not going to do both of them. We'll maybe do one of them. Let's say maybe we do example 9. Okay. But there is extra here in case you want to practice for the exam or just to feel more fluent with the stuff so that you're, more prepared for that next class. A squared in this case for number 9 is 16, so A equals 4. U squared is x squared, so U is just x. I actually don't need chain rule, or I don't need U sub here because du and dx are the same, okay? But I could write this as the inverse tangent of U over A, right? So U is going to be x over A, which is 4, plus C. All right, and you could follow a very similar structure. For example, 9, right? All we've done is swap that 9 with a 16. All right. Well, we've got a couple last examples right here. I think that example 10 is definitely a juicy question, right? Sometimes the bounds make us a little bit nervous. So I do want to take some time to talk through some of the trig values that maybe we don't know as well off the top of our heads, okay? So in looking at this question, we can see that we're going to end up with an inverse tangent. And in fact, we're only going to have inverse tangent of x, all right? Because in this case, A is 1 and U is x. And so there's not a lot to do other than follow the formula. So we get our inverse tangent of x. But we have to plug in root 3. And then separately, we have to plug in root 3 over 3. And I always find that students struggle with the tangent values because they're not actually on our unit circle. We have to like divide things on the unit circle to find them, right? And so if we think about what this is asking us to do, this is saying, find the inverse tangent of root 3. And you're going to subtract the inverse tangent of root 3 over 3. Can someone do a quick Google search for me and tell me what my angle restrictions are for inverse tangent? Good, good, good. So our theta, our angle, is still going to be between negative pi over 2 and pi over 2. The difference here is that inverse tangent is restricted to just between those values. Like we're not going to include them. All right, so there's intentionally no equal sign under there. It's just greater than negative pi over 2 or less than positive pi over 2. Okay, and that's going to be true for all inverse tangent. Inverse cosine is different though, so I would maybe take a look at that and see what that is. All right, even though we don't typically see inverse cosine in some of the work we do in calculus, it is nice to kind of know which trig, inverse trig, has which restricted range. All right. So here's the tricky part about this. The first part to this one is asking you to find an angle such that the y divided by x value equals √3. Right? That's what that's asking us to find. Now it's hard when we have a bunch of like square roots and fractions, but I would encourage you to just practice dividing those fractions. Practice dividing your y over x and see what you get. Take the time to make that pattern happen for yourself, okay? But we'll find that if we go to the y or the angle of pi over 3, that will satisfy the first term. And then we want to try and find an angle such that the y over x value is going to be √3 over 3. And it turns out that that angle is going to be pi over 6. Okay. That means at the end of the day, we're really just combining two fractions that we have to make them have a common denominator. And that area between the curve and the x-axis from that bottom bound to the top bound is pi over 6. Okay. Are there any questions about how we're getting pi over 3 or pi over 6? All right. Well then, I do believe that example 11 is actually much more simple than example 10, all right? So I think a good time to sort of practice that substituting in of values, but I will tell you your final answer should be pi over 8 for example 11, okay? And so that, my friends, brings us to the end of chapter 5 that we are covering, right? So this is 5.7. This is the end of chapter 5. And so let me go ahead and pause the video right here.